Blocks A and B are pressed together with a spring between them. When the blocks are released from rest, the spring pushes the blocks apart so that the 75 hundredths of a kilogram block A moves up the 30-degree ramp to the left, and the 0.25 kilogram block B moves to the right at a velocity of 3 meters per second. Assume friction is negligible. Which of the following is the best estimate of the maximum distance d that block A slides up the ramp? So pause this video and see if you can figure that out. All right, now let's just first think about what would happen intuitively. So we have A and B. You could imagine you're squeezing them together, so you have that energy stored in that spring. And then when you let go, we know that B moves to the right, and you would intuitively think that A would move to the left. And it seems like the law of conservation of momentum is going to be at play here. Because if the system of A and B is initially at rest, each of these blocks' velocities are 0, doesn't matter what their masses are, that means that the total momentum for the system of A and B is going to be 0. So even after we let go and B moves to the right and A moves to the left, the total momentum of the system should still be 0. And so maybe we can use that to figure out what A's velocity is as it's sliding to the left horizontally. And then using that velocity, well, we could think about what's its kinetic energy. And then if we know its kinetic energy, we could think about, well, as it goes up the ramp, that kinetic energy is going to be turned into potential energy. And so how high up the ramp would it go? And then from that and that angle, we could figure out our distance. So let's do that. So let's start off with the law of conservation of momentum. We know that after releasing, A's momentum plus B's momentum should add up to 0 because the sum of their momentums was 0 when they were at rest together, when they were compressed. So what we could say is the momentum for A is going to be A's mass. So let me write it right over here. So 0.75 kilograms is A's mass times its velocity. Well, we don't know what this is. Let's call this velocity or final velocity for A, and that's going to be in meters per second, plus B's mass, which is 0.25 kilograms, times B's velocity, well, that's going to be 3 meters per second, times 3 meters per second. This should be equal to 0. And so now we just have to solve for that. And so what do we get? Let's see. If we subtract this part from both sides, we will get, and this is just 0.75 kilogram meters per second, so we'll get 0.75 kilograms times the A's velocity after it gets released is equal to negative 0.75 kilogram meters per second. And so if you divide both sides by 0.75 kilograms, on the left, you're just going to be left with the velocity of A. And on the right, you would be left with negative 1, and then the kilograms would go away, negative 1 meters per second. So A's velocity as it lets go from the spring, or as it loses contact with that spring, is going to be negative 1 meters per second. Now, what does the negative mean? Well, if to the right is positive, 3 meters per second, then to the left is going to be negative. So it's going to be moving to the left at 1 meter per second. So let's use that information to think about how far up the ramp it's going to go. And we're assuming that friction is negligible and nothing really interesting happens here, although we know in the real world it might bump a little bit, but we're just going to assume that that's not going to be a major factor. And so all of that kinetic energy, when it's moving to the left at 1 meters per second, is going to be converted to potential energy at some height. So let's say that once all of the kinetic energy turns into potential energy, A is at an altitude of h. So what's its potential energy going to be at that point in time? Well, it's going to be the mass of A times the gravitational field, roughly 9.8 meters per second squared, if we want to be even rougher, say 10 meters per second squared, times that height. So that's going to be once all of our kinetic energy has been turned into potential energy. Well, this should be equal to the amount of kinetic energy we had at this point right over here. Well, what is that going to be? Well, that's going to be 1/2 mv squared. So it's 1/2 times the mass of A times the velocity of A squared. So the velocity is negative 1 meters per second, and then we're going to square it. Well, we could divide both sides by the mass of A. Negative 1 squared is just going to be a 1. So this is just going to be a 1 eventually. And so you're left with, and then we can divide both sides by G, and we see that our height is equal to 1/2, and then we're going to have divided by G, and then this is going to be meters. And so what is this going to roughly be? Well, h is going to be approximately, let's say that g is approximately 10 meters per second, because they talk about estimating here. So this would be 1 over 2 times 10, and then we're going to get meters. So it's going to be 1/20th of a meter. So h is approximately 0.05 meters. So you might be tempted to say, oh, look, there's an answer there. But remember, they're not asking us this h. They're asking us this d. And so here you have to use a little bit of trigonometry, where we say, okay, what trig ratio deals with the opposite of an angle and the hypotenuse? This is a right triangle right over here. Well, that would be sine. So sine of 30 degrees would be equal to the opposite side, which is h, over d. We know that h is 0.05. Sine of 30 degrees, if you don't have a calculator, this is a good one to know, is 1/2. So you have 1/2 is equal to 0.05 divided by d. We can multiply both sides by d, and then you'll have d over 2 is equal to 0.05, or multiply both sides by 2, and you get d is equal to 0.10, or I could say roughly equal to, since we are estimating. We had an estimate for g there. And then this is choice D, right over there.